In this video, we solve an application problem. This is for applications of first order ordinary differential equations. And this particular problem happens to be a mixing problem. It comes from Fundamentals of Differential Equations, 7th edition by Nagle, Saff, and Snider. The problem statement says, a brine solution of salt flows at a constant rate of 4 liters per minute into a large tank that initially held 100 liters of pure water. So I'm going to draw a picture. I think that's always a good idea. Start here. It's a very large tank. And initially, sometime, it holds 100 liters of water. And they said that a brine solution, that's a saltwater solution, flows at a constant rate of 4 liters per minute into the tank. So we've got 4 liters per minute going in. And it initially held 100 liters of pure water. Then the question says, or the problem statement says, the solution inside the tank is kept well stirred. So that just means that there's no big chunks of salt over here that aren't over here. Everything is evenly distributed. The concentration is identical throughout the entire solution. So it's well stirred, and it flows out of the tank at a rate of 3 liters per minute. And that's significant. You've got 4 liters per minute going in and 3 liters per minute going out. So that means every minute you're actually gaining a liter. You're gaining 1 more liter in the solution. So 1 minute later, you're going to have 101 liters in here. And 2 minutes later, you're going to have 102 liters in there, and so on. So it's significant that those are different from each other because it changes the volume of the solution inside. Okay. What else? It says, if the concentration of salt in the brine entering the tank is 0.2 kilograms per liter, so you got 0.2 kilograms in every liter, and you've got 4 liters going in every minute. The question says, determine the mass of salt in the tank after t minutes. When will the concentration reach 0.1 kilograms per liter? Now, anytime you're dealing with a mixing problem, we're just going to use this very simple model. And it's really just a framework because we don't really have anything for this rate in or rate out yet. That's something that we need to come up with ourselves. But this is what it says. The model says that the rate of change of the amount of salt in the tank per unit time is just equal to the rate of salt going in the tank minus the rate of salt going out of the tank. It's common sense. So we just need to find the expression for the rate going into the tank and the rate of salt going out of the tank. And then you always have an initial condition as well. This is telling us the amount of salt at some point in time is equal to some amount. So that's usually in the problem statement somewhere. So what I like to do when I'm solving a problem like this is I draw a picture. I write down the appropriate mathematical model. Usually this is told to you somewhere. There's usually a sentence that you have to interpret, but with every mixing problem, you're going to use this model. The rate of change is equal to the rate in minus the rate out. So we've got that. And now we just need to find the rate in and the rate out and the initial condition. And I guess I should do one more thing before we go on. Let's define the variables as well. We're saying A of t is the amount of salt in the tank. At time t. Now, because of the units that are used, because we're told that the concentration of that brine solution entering the tank is 0.2 kilograms per liter, that kilograms there tells me that I should measure the salt in the tank in kilograms. So those are our units. Now, t we know to be time. But we'll also look for indicators in the problem statement for the units for time. Since we're told that 4 liters per minute, that's the volume of solution entering the tank per minute. That's what we've got going on here. Since those units in the denominator are minutes, the time must be measured in minutes. And if A is measured in kilograms and time is measured in minutes, dA dt, remember how that's defined from Calculus 1, That's the limit as delta T approaches 0 of change in A over change in T. So that's a change in the amount of salt in the tank per change in time. So this is also going to be in kilograms, or since this is in kilograms and this is in minutes, this is going to be in kilograms per minute. And everything has to be dimensionally consistent. So when you look at this rate over here, this is kilograms per minute. So we need a rate in kilograms per minute, and we need a rate out in kilograms per minute. Actually, the rate in is pretty simple. It's actually right here. We know that we've got 4 liters of solution entering the tank every minute. And we know that there are 0.2 kilograms of salt in every liter. So if I've got 4 liters entering and there are 0.2 kilograms in every liter, it makes sense that I would be adding 0.8 kilograms every minute. And that's exactly what you get. If you multiply these two together, the liters reduce and you end up with the rate in of 0.2 kilograms per minute. Now over here, we don't have the concentration. The concentration is going to depend on time here because we're adding salt to the tank and then we're mixing everything up and then we're saying, okay, what's the concentration of the solution entering the tank, or the solution leaving the tank? We're assuming that maybe we've got a little spout over here. What's the concentration of that solution leaving the tank that's leaving at this rate of 3 liters every minute? So in order to figure that out, well, let's just think it through. We're going to use something very similar to what we have here. We just need that concentration of the solution in the tank at time t. So let's think about it. I've got trying to find my rate out now. And I'm going to multiply that by 3 liters per minute in order to get some number of kilograms per minute as my rate out. Well, in order to get that, I need a concentration here for the solution in the tank at time t. In the numerator, I'll have the kilograms of salt that are in the tank at time t. In the denominator, I'll have the number of liters of solution in the tank. Now the fact, well, actually I'll do this denominator last and say, well, how many kilograms of salt are in this tank at time t? Well, we don't really know, but we do know that the amount of salt in the tank at time t is represented by this variable a of t. So we're going to have a of t kilograms. I don't know what a is. I'm trying to find a, but I can substitute that variable there because that is how many kilograms of salt are in that tank at that time. Now to find the volume of the solution in the tank, this is a little bit trickier, but I alluded to it earlier when I looked at the volume of solution entering the tank per minute and the volume of solution exiting the tank every minute. If I've got 4 liters per minute entering the tank and 3 liters per minute leaving, that means every minute I'm gaining another liter. So I start with 100 liters, and then 1 minute later, I've got 101 liters, and then 2 minutes later, I have 102 liters, and 10 minutes later, because this happened 10 times, I'm adding 4 times 10, I'm adding 4 liters per minute, 10 times, and then at every single minute, I'm taking out 3 liters per minute as well. And so every minute, I'm gaining another liter. So if t is time in minutes, we're just going to add a t there. This is the number of liters in that tank, because if I'm adding 4 liters per minute and subtracting 3 liters per minute, every minute I get another liter in the tank. And that's equivalent to saying that the number of liters is the number of liters it started with, which is 100, plus, well, however many minutes it's been, because I gain 1 per minute. Okay, so that's my rate out. I'm going to multiply so that the liters cancel, and you end up with 3 times A over 100 plus T, and this is kilograms per minute. So that's my rate in and that's my rate out. We just subtract those to get our differential equation. So dA dt is this. It's the rate out, or rate in, excuse me, minus the rate out. We also need an initial condition. Let's go back to the problem statement. This is about salt, amount of salt I have in the tank. So up here somewhere, there must be telling us how much salt is in the tank initially. Ah, here it is. Initially, the tank held 100 liters of pure water, no salt. So if we say that at that moment, when we started adding this saltwater solution to the tank, that's T equals 0. There was no salt. The amount of salt in the tank is 0 kilograms. So this is the time and the corresponding number of kilograms of salt at that time. So now you've got a differential equation and an initial condition, and you can solve the initial value problem however you want, whichever way is appropriate, given all of the methods that we've learned so far. So let's look at those methods. So the methods that we've studied so far are these. We can solve separable differential equations. We can solve first order linear differential equations with an integrating factor. We can solve homogeneous polar differential equations. We can solve Bernoulli differential equations. And we can solve exact differential equations. So we just ask ourselves, we look at this list and we ask ourselves, well, which one of these is this? It doesn't look exact. It doesn't look Bernoulli because that would require an a to some power other than 1. It may be a homogeneous polar, but I don't think I want to use that method if I could use separable or first order linear. I believe this is separable. I could write this as separable if I got a common denominator, but it's also first order linear. This can be written as dA dt plus a function of t times a equals a function of t. Either one of those is fine. I'm going to use the first order linear method because that's the one that appeals to me right now. But if you wanted, you could get a common denominator and then separate those variables if you prefer. That's fine. You're going to get exactly the same answer. So I will rearrange that differential equation by adding this term to both sides and then factoring out the a. And now you see you've got the derivative plus a function of t times a equals a function of t, and it's first order linear. So whenever we solve a first order linear equation, we'll start by solving the dE. Whenever we solve a first order linear equation, the first thing we do is identify p and compute its antiderivative. So our p of t is the function in front of the a. And the antiderivative of p of t is the antiderivative of 3 over 100 plus t. Well, that can be found pretty easily with a u substitution. If I let u equal 100 plus t, du is just the derivative of that, which is 1, times dt. So this becomes the integral of 3 over u times du. And the antiderivative of 3 over u is 3 times the natural log of the absolute value of u plus c. We'll choose that c to be 0 because we don't need infinitely many integrating factors. We just want the 1. And then we back substitute. Replace that u with 100 plus t. So we had 3 times natural log of u, which was 100 plus t. plus c. That's our antiderivative, and we're going to choose c equals 0 because we only need a single integrating factor. Now we're going to define the integrating factor. This way, it's e to the integral of p of t power. Now you can't simplify this as it's written. A lot of students want to cancel that log and that e, but you cannot cancel those unless you have a 1 in front of the logarithm, not a 3. So you have to use this old rule from algebra class. If you've got a constant in front of your log, you can bring that inside. That'll be log of a to the n. So this turns out to be e raised to the natural log of the absolute value of 100 plus t cubed, and exponentials and logarithms with the same base undo each other, and we would get this. Now let's think about the problem here. We are filling a tank with a brine solution starting at t equals 0 and just going on from there. So given the context, t is never going to be negative. T will always be greater than or equal to 0. And if t is greater than or equal to 0, 100 plus t is certainly greater than or equal to 0. So this can simplify to 100 plus t quantity cubed for our implied domain of t greater than or equal to 0. So we found our integrating factor. Whenever we're solving a first order linear differential equation, we take that differential equation and we multiply the whole thing by the integrating factor. Every term gets multiplied by that integrating factor. So we multiply by 100 plus t cubed here, and here, and here. And then we simplify as much as we can. One of these will reduce with one of those, so we'll have 100 plus t squared there. Now remember, if you've done everything correctly, the reason that we multiplied by that integrating factor was to get us here, to get us this. So if we've done everything correctly, the left-hand side should be the derivative with respect to t of the dependent variable times your integrating factor. That's what Bernoulli said. He said, if we multiply by this, then you can say that the left-hand side is the derivative of this product, and that is going to get us 2 steps away from getting that dependent variable by itself. So we multiply the differential equation by the integrating factor, and then we say, well, if that's true, then the left-hand side is this derivative. And then if that's true, and you're trying to get a by itself, you just have 2 operations to undo. We multiplied it by something, and then we took a derivative. To undo that, we'll take an antiderivative of both sides with respect to t. And the antiderivative of the derivative is the original function. And then over here, we can evaluate this antiderivative using a u substitution if you prefer. Since I've got a function nested inside another function, that's probably the simplest way to evaluate this. This is such a simple u substitution that this is one many students might do in their head. If you don't want to do it in your head, you can do it this way. If u is 100 plus t, du is just 1 dt. So this is just a u cubed times a du there. So we've got the integral of 0.8 times u cubed times du. And then we anti-differentiate. So you bring the constant down, add 1 to the exponent, and divide by the new exponent, and add c. 0.8 divided by 4 is 0.2. And don't forget to back substitute. U is 100 plus t. And all of that was part of anti-differentiating both sides to get our dependent variable times the integrating factor by itself. And now we want to get that dependent variable by itself. So we'll just divide everything by the integrating factor. Now, a lot of students make the mistake of not dividing this constant by the integrating factor. Actually, we used c for something else. I'll call that one c1. The c needs to be divided by the integrating factor as well. So now we've got a of t. This is the general solution of that first order differential equation. And you've got 3 of those down there and 4 of them up here. So 3 of them reduce. If you want, you can say this is c1 times 100 plus t to the negative 3. That's fine. This is the general solution. And it would be defined on 0 to infinity or 0 to some appropriate upper limit, which is related to the volume that tank can hold. We don't actually know how much the tank can hold. We just know that it's a large tank and it initially holds 100 liters. So provided that it's a very large tank and you can just keep adding and adding and adding, t could go to infinity, but there's probably, well, there is certainly an upper limit on that t value, but it depends on the volume of the tank, which we don't know. Now this is the general solution. This is not the solution of the IVP, because if you ask me for the amount in the tank at time t now, I would have to give you an answer in terms of an arbitrary constant, and I don't want to have to give you an answer with an arbitrary constant in it. I'd like to tell you this many kilograms are in the tank after 10 minutes, this many kilograms are in the tank after an hour and a half, or whatever. So in order to answer that question or answer questions like that, I need to find the value of c, the c1. I can use the initial condition to do that. And that's a of 0 equals 0 to find c1. So we will evaluate this expression at t equals 0. Because a of 0 equals 0 means that when t equals 0, this whole quantity must be 0. So we evaluate that there and we set this equal to 0. That's the a value. Because a of 0 equals 0 means when t equals 0, a equals 0. So now you've got this equation that you can solve for c. So we're here trying to solve for c. So we just end up with 2 times 100, move that decimal over twice, you're going to get 20, plus c1 times that 100 to the negative 3 equals 0. So if you prefer, you could call this c equals, or c1 equals negative 20, or c1 over 1000, or 100 cubed, excuse me, equals negative 20. And then if you multiply both sides by that 100 cubed, you're going to get negative 20 times 100 cubed. And you could write out all those zeros if you want to. I don't think I will. I think I'll just write the answer this way. So a of t is equal to 0.2 times 100 plus t plus C1, which was negative 20 times 100 cubed times 100 plus t to the negative 3 for t greater than or equal to 0 and then up to some value of t. Okay, now the first question said, determine the mass of salt in the tank after t minutes, and that's what we just did. We set up the differential equation. We said rate in minus rate out is that. Got this initial condition, so we solved the IVP. We said that's a first order linear equation. We used an integrating factor to solve it. And we did all the work and we solved it. And eventually we not only solved it, but we used the initial condition to find the solution. So this is the particular solution. This is the answer to the first question. And to get it, we substitute C sub 1 into the general solution. Okay. Now the second part of the question says, when will the concentration reach 0.1 kilograms per liter? Now that initially seems like a tough thing to compute, but actually we've already computed the concentration. This is the definition of the concentration. The concentration is the amount of salt in the tank per liter in kilograms per liter. The amount of salt in the tank is A of T. And the number of liters in the tank turned out to be 100 plus T liters. And we want to know, when is that equal to 0.1 kilograms per liter? Well, that's easy enough to solve. It's just an algebra problem. So you're going to cross multiply. You have A of T equals 0.1 times 100 plus T. And A of T turned out to be this expression, 0.2 times 100 plus T minus 20 times 100 cubed, and that's a 100 plus T cubed in the denominator. I think I'll write it like that this time. And that is equal to this. I'm focused right here. This is my A of T, and that is my right-hand side. Well, in order to solve this, to make it simple to solve, I'll get a common denominator on this left-hand side. So I'll multiply this one by 100 plus T cubed over 100 plus T cubed, which would make that a 100 plus T to the fourth over that. That over that simplifies to that. You should check if you're not sure. And then I'll multiply both sides by this denominator. So it'll make it really easy for me to solve this equation. So I've got 0.2 times 100 plus T to the fourth minus 20 times 100 cubed equals this expression times 100 plus T squared, or 100 plus T cubed. I've got one of these factors over here, and I've got 3 of them down there, so I'll have 4 of them total. And then if we subtract this from both sides and then add that over, what we end up with is this. We're going to have 0.1 times 100 plus T to the fourth over here, minus this equals 0. And if I add that to the other side, I'll have 20 times 100 cubed over there. Then to get rid of this 0.1, I will multiply both sides by 10. So we have 100 plus T to the fourth is equal to 200 times 100 cubed. To get T by itself, we'll take the fourth root of both sides. Normally we would do a plus or minus. for this algebra problem. Then you've got 100 plus t is equal to plus or minus the fourth root of 200 times 100 cubed. And then to get t by itself, we'll subtract 100 from both sides. Actually, I think I'll just stay here on this piece of paper. So we have t equals plus or minus the fourth root of 200 times 100 cubed minus 100. Now, normally I would have the plus or minus if I'm just solving this algebra problem, because a positive number or a negative number raised to the fourth would still give me, the number over here, this 100 plus t to the fourth on the other side. But we're talking about time here, and we're talking about an amount of salt in a tank, and we started adding salt water to a tank at time t equals 0. So this result is supposed to be positive. So typically I'd keep that negative if I'm just doing algebra, but I'm solving an application problem. So I want the positive fourth root of 200 times 100 cubed, and then we'll subtract 100 from that, and that'll give us the time. So we have 200 times 100 cubed. And then I will raise that to the 1/4 power. That's the same as taking the fourth root. And then we subtract 100. Remember, time was measured in minutes. So it looks like it's been about, or it will take about 18.9 minutes for the concentration of salt in the tank to go from 0 kilograms per liter to 0.1 kilogram per liter. And that's it. Now we've answered all of their questions. And I'll see you in another video. I will show you a different application of first order differential equations in the next video.